È un enorme piacere avere qui Lucia Caporaso, Lucia ci conosciamo, sono 35 anni quasi, è sicuramente una dei geometri algebrici italiani e più in vista a livello internazionale, a cominciare dalla tesi di dottorato che discusse nel 93 a Harvard, e mi ricordo ancora, ero presente alla discussione, non so se ti ricordi, e c'era anche e c'era anche, cosa notevolissima, David Mumford, che era stato un grandissimo geometra algebrico, e all'epoca ormai da più di 10 anni si occupava di questioni di visione, però venne perché Lucia nella tesi di dottorato risolse un problema a cui Mumford aveva lavorato per del tempo, quindi una cosa. Dopodiché ha avuto una carriera molto brillante, è stata postdoc a Harvard, poi dopo una professore all'MIT, assistant professor all'MIT, poi per nostra fortuna ha deciso di tornare in Italia, dal 2001 è professore ordinario a Roma 3. Ha parlato in sostanzialmente tutti i convegni più in vista, sicuramente di geometria algebrica, è stata anche invited speaker all'ICM nel 2018, ha fatto dei lavori molto molto importanti di varia natura. Ultimamente si è occupata, ultimamente un po' di anni oramai, si è occupata più che altro di queste cose che si chiamano geometria tropicale, un termine piuttosto buffo, che non è quello però di cui ci parlerà. Parlerà di distribuzione di punti su varietà, che è una cosa su cui ha scritto un lavoro importantissimo con Joe Harris e Barry Mazur, e ci renderà partecipi degli ultimi sviluppi, quindi ringraziamo davvero perché ci ha fatto l'onore di essere presente.
Thank you, Angelo. Actually, it's my honor to be here. Thank you very much for the invitation, and thank you for the presentation, the very nice presentation. As Angelo just said, I will speak about, I will give an overview of progress of about 40 years of progress up until very recently, this year and last year, about the certain arithmetic properties of algebraic varieties, especially curves, and their interaction with the geometric properties of algebraic varieties. So what do we mean by arithmetic properties? For our algebraic varieties intrinsically have a double nature, an arithmetic nature and a geometric nature, by which I mean that our varieties will be usually defined over the field of rational numbers, which is, of course, a subfield of the field of complex numbers. And so when studying our varieties over the field of rational numbers, we would be thinking that we're doing arithmetic. And of course, over the complex numbers, this will be geometry. This is somehow the way we speak about these things. Now, as you see, I left some space, so it's much better to include in this picture more fields. This is what we learned. So one of them is the algebraic closure of the field of rational numbers. And between the two, it's useful to consider all finite extensions of Q. Those are called number fields. So here we will consider finite extensions of Q. So this is a number field, usually called a number field. So this is a finite extension. A is an algebraic number. You add A to Q and you have a number field. So these will be the fields we will be looking at. Algebraic geometry classically has to work over some field. So all of them will be in the talk. So I will use the letter F to mean all of them, okay? And I will specify which. So as I said, algebraic varieties have this somehow double nature. What do we mean by that? So what are algebraic varieties? Andrea asked me to keep the talk accessible for at least part of it for a general audience. So let me tell you what algebraic varieties are. So we can think of algebraic varieties as embedded in some ambient space or as abstract objects. When we think of them as embedded in some ambient space or inside, we think of them as concrete objects. They're associated to the set of zeros of a certain number of polynomials. Usually it suffices to take a finite number of polynomials. So we take, we take some polynomials with coefficients in Q, a set of polynomials, so some finite set of polynomials in a certain number of variables. So this is just a subset. We will know small, usually a finite subset. And the zeros of these the common zeros of these polynomials are subset in Q to the n. So the set of zeros of common zeros of P is of course a subset of Q to the n. This is the underlying set to an algebraic variety. An algebraic variety is more than just a topology. Is more than a set. It has a topology. Is more than just a topological space, as I will say more clearly later. But still, let's focus on the topological space. So this is a subset in the set of rational numbers, and since the rational numbers are contained in the set of complex numbers, for any f, we have a set, a subset in f to the n. In particular, so, and then of course, in C to the n. Now, the reason why I'm doing this is that I want to explain how this is not the best ambient space, the best type of ambient space that we want to look at. The reason is that this space, you see, when you look at C to the n has a topology, the analytic topology, which we know very well. And we know this is not compact in the analytic topology. Let me write it in analytic topology, because we will have more topologies. But the analytic topology is just so very important. And so this space is not compact. And it's better to compactify it for several reasons. In some sense, when we look at our algebraic varieties inside Qn or Fn, it's like looking at them just locally. The analogy in general mathematics is think of the difference of doing Euclidean geometry. This is okay when you are locally around you, but when you go to huge scales, Euclidean geometry is no longer sufficient. In the same sense, we prefer to extend this space to the projective space. The projective space over C is compact in the analytic topology, and we want to use this as ambient space. So then this will mean that from now on, our algebraic varieties will not be given by, so we subset of projective space, which is of course the set of n+1 tuples of complex numbers modulo the usual equivalence relation that two tuples are give the same point if they are obtained one from the other by multiplying all coordinates by the same constant. And in here we will have the projective space over any field, in particular over Q. The only thing we have to be careful about is that we cannot take as P any set of polynomials, because it doesn't make sense to evaluate a polynomial when you have only homogeneous coordinates. It makes sense only if it does never make sense. It does not make sense, and it doesn't even make sense to say when a polynomial vanishes. But it does make sense to ask when a polynomial vanishes if the polynomial is homogeneous. So let me just correct this on the board. Instead of taking any set of polynomials, we will take homogeneous polynomials. And since we have an extra variable up there, we need one extra variable. Let me just do this. And then the set of zeros will be a subset in here. Okay, now that I told you what an algebraic variety is, let me give you some examples. So let's start looking at things more in details. So let us look at a very famous example. I'm sure you will recognize it. So let's take a plane curve. Let's take a polynomial with coefficients in Q. This is a polynomial in 3 variables. And D is some integer at least 1. Okay, so we have lots of them. The set of zeros of this thing is a subset in projective space. This is a homogeneous polynomial of degree D. Let me call it C. Now the question is, where do we want to look at this? Do we want to look at this over the rational numbers, or do we want to look at this over the complex numbers? So let me do both things, but we do need a notation to distinguish, okay? So the notation we use is the following. So I deliberately use the letter C here. This usually is meant to be over the complex numbers, the biggest one. But so if we want to study this over the rational numbers, we write C of Q. And since this depends on D, let me put a D here for clarity. So CD of Q is just a set of X, Y, and Z in P2Q where that equation is satisfied, okay? Okay, this is a set. We can try and describe it. Okay, let's do that. This depends on the degree. Let's start with the simplest case. If the degree is 1, X plus Y minus Z, this is a line. This is something we learn very early in our life. So this has infinitely many points. In fact, it has as many points as Q. So this is a countable infinite set. This is if D is 1. If D is 2, we are in projective space, so coordinates are given up to constant, and so we can assume that X, Y, and Z by clearing denominators are integers. So if D is 2 and these 3 things are integer, X squared plus Y squared equals Z squared, these are all the Pythagorean triples. So it becomes much less trivial, but still is also countably infinite. Okay, if D is greater or equal than 3, there is obviously some point in here, because if you take Z equal to 1 and 1, 0, and one of the two equal to 0 and the other one equal to 1, you have 2 points. So this is certainly not empty. So you have the point 1, 0, 1, and 0, 1, 1. And is there anything else? And the answer is no. But this is a highly non-trivial statement. This is the Wiles theorem of the Fermat's last theorem. So let me do that. So this is Wiles 1995, proving something conjectured by Fermat in 1630, I believe, 7. Not actually conjecture. Fermat thought he proved it, but as you probably know, he didn't really. At least we think he didn't. And it took so many years to prove it. And this is a major achievement of last century's mathematics. The other thing I want to do before I finish discussing this example, I want to discuss it over the complex numbers. But I don't want to forget. The point I want to make is that even though this is a very simple equation, and the problem is actually a seemingly simple one, it is very hard. It is very hard to solve this type of equations over the rational numbers. Okay. In fact, it's known that if you ask for the general problem, is it true that any such equation is solvable? It's known that this is a non-decidable problem. This is getting us too far. So let me just say these equations are very hard. It is usually difficult to describe such curves when they are even when they are in projective space. So what about the complex? What happens over the complex numbers? The situation is quite different. So over the complex numbers, we use the same notation. Same thing, okay? This is something, this is much easier to solve because C is algebraically closed. It's much easier from the computational point of view, but from the geometric point of view, the picture is completely different because this is a set that is easily seen to be in bijection with the set of complex numbers. So this is an uncountable, has the same cardinality as the set of complex numbers, and hence it has dimension 2 over the real numbers because the complex numbers have dimension 2 over the real numbers. So this is a compact surface over the real numbers. And its shape is as follows. If D is equal to 1, it's a sphere. This is just a shape, okay, it's just a way of introducing geometry. It's just a sphere. And the same is true if D is 2, actually. If D is higher, then you get an orientable surface with positive genus. So you would get an orientable surface of genus. The genus is a function of the degree. Is the genus of this is D minus 1 choose 2. In fact, this case, yeah. So it's an entirely different story. But it tells you that there is geometry and arithmetic, and it enables me to define the genus of any. This is called a plane curve. The genus of any plane curve, provided the polynomial that defines the curve is not singular, so the 3 derivatives do not vanish simultaneously at the same point. Then the genus is always this function of the degree. All right. Okay. And for this example, the point, as I said, was to convince you that it could be used, and in fact, it has been useful to look at curves, not in projective space, but abstractly. And the same holds for varieties of any dimension. So let me explain what an abstract variety is. Okay, again, over any field, F, that is Q, the complex numbers, a number field, etc. So what is an abstract variety? I'm not going to give you the definition. I'm going to tell you how you should think of it. It's actually nothing very special. Something like this happens in many other fields. So a variety V, I will use V for a variety of any dimension, including a curve. For me, this would be a projective. I will explain the meaning of this word, smooth, of dimension something, n. So this abstractly, that is without putting it into any ambient space. You can put it in many ambient spaces if you want, but you don't need to. You can look at it just abstractly. This is locally, has a finite covering by open sets that look like open sets of projective concrete varieties, as I basically did not explain. I just told you what they are. But anyway, so it's a finite covering of open subset of varieties of that type, with the additional condition that over C, it is compact in the analytic topology. Just as I said before, we prefer to work with compact spaces because we have a better picture, a global picture. Smooth means that over any point, the tangent space, this is always over C. So this is the geometric version of it. They're all defined over F, over some field F, which could be Q. And hence, they also have a complexification, if you want. You can think of this as a complexification. For every point, little v in V, the tangent space is a copy of C to the dimension of the variety. This is, so you should think of this as just a smooth thing. That's just what the word says, okay? So for example, a curve has dimension 1. Is a variety, smooth projective variety of dimension 1, and I will just call that a curve. And now we want to investigate the arithmetic properties of abstract varieties. So we want to investigate rational points of algebraic varieties. Question. Is there any question? No. No, I'm not allowing any singularity. Just smooth. Okay? So the picture for curves is all we have. We don't allow anything like this. No, this is not smooth. We could, but we don't. Okay, and the same in higher dimension. Now, as I was saying, we are interested in arithmetic properties of these objects. So we want to know about rational points. So now we do not have an embedding of our variety in a projective space. So what do we even mean by rational points? So let me tell you what we mean by rational points before we start talking about them, right? So we denote, again, as before, we denote by V of F, the set of F rational points that should extend that definition I gave in that example. So we call this, so you can think of F as Q, the set of Q rational points, for example. So these are the set of F rational points. But what are they? So this is just a mouthful, right? For now, it doesn't mean anything. And so here is how you define them. First of all, what is a point in algebraic geometry? As I said before, an algebraic variety is not just a set, not just a topological space. It comes with a certain gadget of functions on it. Otherwise, it wouldn't be an algebraic variety. So it's a topological space plus a certain gadget of functions, which we call a sheaf, but we don't need to talk about that. But what is a point then? A point over F, over our field F, is what? Is the point as a topological space, and the set of functions you can think we will endow the point with. So what could they be? Well, the functions on the point defined over F will be the constant functions with values in F. So if the point is over Q, the functions are over Q. If the point is over C, the functions are over C. So you see, you get lots of different points. Okay, not all points are equal. And the notation we use is a bit ugly, but the notation is this, is denoted by spec of F, a point. This is a point over F in algebraic geometry. And now what are rational points? What are F rational points? This is a variety defined over F. This is a variety defined over F. If you think about it just a little bit, it makes perfect sense to define rational points as follows: homomorphisms from spec F to V, where homomorphisms here means in the category of algebraic varieties. Okay, so this is the definition of rational points in general. That is, not in general, for abstract varieties. And if you put your variety in projective space, which you can, you find the old definition. That is, the rational points are the ones that admit all coordinates in the field you're looking at. So you put your variety V in projective space over the complex numbers of dimension whatever, it doesn't matter. The rational points, or the F rational points, are the ones that admit all coordinates in F. But as the example before was somehow suggesting, it may be more productive to look at varieties abstractly rather than in projective space. Okay? And in fact, one or another of the most amazing theorems of, I guess, almost 40 years ago, so before Weyl's theorem, another really amazing theorem tells us about rational points on curves. So this is a theorem which I will state in a slightly different way than, so let me do it. So let's see a curve of genus G over, say, Q. And then there are two possibilities. Either the genus is 0 or 1, or it is greater than 2 or equal to 2. In this case, there exists a number field. Remember, a number field, I erased it, is a finite extension of Q, is an algebraic finite extension of Q. So let me write a number field, which is usually denoted by K. Let me just remind you for a moment that this is something of this type, such that the set of rational points of C over K, the set of K rational points of C, is infinite. and hence countably infinite, because this is a number field. This is not that hard. The hard part is the next. The hard part is that if the genus is at least 2, then for any number fields, for any number field as above, the set of rational points is finite. Now, this is a big, huge theorem by Faltings. Faltings proved this in 1983. And this is also called the Mordell conjecture. So he proved the Mordell conjecture. See, again, this has been proved. It's been easier to prove this than to prove the Wiles, the Fermat's theorem. And let me tell you how one approaches such a thing, okay? How does one do that? As we said, so we don't want to put the curve back into projective space because we know it just doesn't make things easier. But we can do something slightly different, actually very different, but still it consists in putting the curve inside some ambient space, which we can work with. And the ambient space, so the context of the proof of Faltings and also many others, because this theorem has many proofs. I can start naming huge names like Weil. He didn't prove it, but he provided the instruments to prove it. Mumford, he didn't prove it, but provided the instruments. And then Vojta, and then Tate, and then Neron, and then Bombieri. I don't know. There are at least five proofs for this. And all the ones I know, and I think all the ones that exist, all begin in the following way. They take the curve and place it in an ambient space that is called the Jacobian of the curve. This is called the Jacobian of C, which is something quite easy to define. This is actually quite amazing because you define, well, quite easy. Well, it is actually quite easy. You define it as follows. You take the free abelian group on the points of C. So if you're looking at the curves over K, these would be the K points. If you're looking at the curve over C, etc. So the same thing. And you take this modulo sum equivalence relation that I will not define, but it is actually quite natural. So this thing is not just a group, it's actually a variety, it's a projective variety, exactly in the sense that I described before. And what's really somehow wonderful is that when you look at this over the complex numbers, so over C, J of C has a very nice shape, is the quotient of CG modulo Z to the G up to isomorphism. So it's something that looks very familiar, but it is projective, it's compact. Okay, so we place the curve inside a compact variety. This is what we call an algebraic, an abelian variety in algebraic geometry, which is also a group and also has a strong analytic structure from this, you see. And that's where you begin to work. This is, I'm not going to tell you to say anything else, but this is where you begin to work. You place the curve inside the Jacobian, and then there's a lot of work to be done. But so here we have this new ambient space, okay? Okay. These are results that are quite classical now. And there are several questions that arise from this. One of them is, well, in 1983, algebraic geometers had quite a fair understanding of, let me say, the word of all curves of genus G. By that time, we understood that curves of genus G could organize all together in a very nice way. And let me tell you something about that. So this is something apparently completely unrelated, okay? But so the thing is that consider now all curves of genus G over all fields, all of them, okay? The only thing we fix is the genus. So we fix the genus, and not to avoid wasting time, let's just say we only want to look at genus at least 2, because that's where things get interesting. As I said, the theorem, I studied in 2 ways for the colloquium, but the really important part is the second. The first is there to give you, a comparison, but the really interesting one is the second. So let us assume that the genus is at least 2. So let's look at all curves of genus G of all fields at the same time. And so then we knew already by that time that there exists a very nice object, which is called MG, is denoted MG, called the moduli space of curves of genus G. The name moduli doesn't suggest much, so just don't think about it. It has a history which could be the topic of a talk. Okay, so it's due to Riemann, but for us, it's really, if you've never seen this, just ignore it. Think of it as space of all curves of genus G. Now, what is this? All right, so there are various incarnations, but the one the one that is enough for our arithmetic purposes is, this is an algebraic variety defined over Q. So it's defined over all our fields. It has nice property. We know what its dimension is. We know that it's irreducible. We know it's connected. We don't care about that. Okay, let me just tell you, so just like you get a feeling that the dimension is 3G minus 3. Okay, just to have a feeling. But what are its rational points? That's what we want. First of all, what do we want to do? So we would like to say that the points of this space, this is a variety, the points of that space are in one-to-one correspondence with isomorphism classes of curves of genus G. This is almost true. So the set of rational points of MG, so these are the points defined over F, are in one-to-one. So this is a set. This parameterizes curves of genus G defined over F up to isomorphism, and that's true. The only thing is that we have now, if you take a curve, think of Q instead of F, that's simpler. If you have a curve defined over Q, 2 curves defined over Q, they may be isomorphic over Q, and that's great. They may fail to be isomorphic over Q, but they may be isomorphic over C, over the algebraic closure of Q. And so this is a problem. This moduli space parameterizes curves of genus G over F up to isomorphism over the algebraic closure of F. Okay, this means isomorphisms defined over F. So MG of F. Yeah. No, because no, the thing is that, yes, okay, I know what you're saying. Okay, if you want, we can discuss about that, but let's say up to, so you have, all right. Yeah, okay. But let me, so if you want, I could take as the stacky point, this is what it is. But this is not the issue. The issue here is this. Okay, this is the issue. But in fact, I'm going to replace this space in a moment, which you know why I am cheating right here, because I'm going to replace this space with a space with level structure. So your comment is right, but I will, how do you say? I will circumvent it in just 2 minutes. So anyways, the point is that the points of this moduli space parameterize curves up to isomorphisms over the algebraic closure of the field and not over the field. So over the complex numbers, we are very happy. Points over the complex numbers are isomorphism classes of curves over the complex numbers, and the same is true over Q bar, of course. But over Q, that's not true anymore. It's very easy to find examples of curves that are not isomorphic over Q, but are isomorphic over Q bar. Very easy, okay? As he was saying, there is a little bit of a problem here. This moduli space is not ideal in the sense that it does not, what we would like is to have a space that not only parameterizes all our curves, but also all our families of curves, and such that every other family of curves can be obtained from this place by base change. This is something that probably means very little for the non-experts, but the point I want to convey is that we have to somehow modify this moduli space. Otherwise, we do not have what we want to have, and that is a universal family. So let me tell you what we want. We want a moduli space, which, as I said, is not going to be MG, but is going to be some little twist of MG. That's an L. I'll tell you what that is. Over which you have a universal family. So this is a fibration over MGL, surjective, all of whose fibers, the fiber over a point, is the curve parameterized by that point, which is not does not happen over MG for reasons that we don't want to get into. So now, and this is where I'm circumventing the problem, I'm going to put an L here, this is the moduli space I will look at. And here, instead of taking the moduli space of curves of genus G, that L means we add a little bit of structure, just a little bit of structure, which is called level L. L is an integer structure, so that we do have a fine moduli space, because these level structure rigidify the curves in such a way that they no longer have automorphisms. So this is a trick. I call it a trick. It's actually a deep point, but it has become completely standard now, which is why I am going over it quite quickly. So here I'm just going to put a little L here, which I hope you ignore. Okay, no, you should. You should. In fact, they don't even do it. I'm just going to state a theorem, and the authors don't even put the L here. They just write MG. Okay, so by here I have to say moduli space of curves of genus G with L structure. If you know what that is, L is a number at least equal to 3. But that's just not. And then everything I said is still true. The only thing that's new, which did not have before, is that we have this. We have a universal family. And not only do we have a universal family, we also have a universal Jacobian. Remember, the Jacobian is important for our arithmetic questions. So to do arithmetic, we need the Jacobian. So we need the Jacobian. This is the universal Jacobian. So these two things are universal in the sense that every family of curve can be obtained by base change from this one, and its relative Jacobian can be obtained by base change from this one. So these are universal objects. Let me not write it. Okay. Now the thing is, we have this nice moduli space of curves that organizes all curves in one big variety. And we even have a universal family by adding something, but this is not a problem. This is so in case you worry, and in fact, I should say that for every fixed curve, you have only finitely many fibers of this family isomorphic to that curve, by which I mean that the map of this thing has a map to moduli space, and this is finite. So up to taking a finite cover of MG, we've solved our problem about universal spaces. All right, so now the question after that theorem came out was, well, we have curves, they all fit together in one family. Maybe also rational points are well behaved. Maybe they also fit in a nice family. Maybe, who knows, right? They're finitely many for every curve. Maybe they're even uniformly bounded. Maybe there is a bound on the cardinality of the set of rational points that does not depend on the curve. Okay, so here is the strongest conjecture that is around and has been around for, I guess, 30 years or so, at least, which is attributed to Serge Lang, and it's the boldest and strongest one. And it says the following: this is the strong Lang conjecture. And says, let's take fixed genus. For every genus, there exists a number that depends only on the genus, such that for any number field K, for which we know that a curve has only finitely many rational points, we'd like to say that every curve of genus G defined over K has at most NG points. Now, this is not quite enough. This is certainly false. If we do that, this is false. But we can do the following. We could say, consider the set of curve C of genus G defined over K, having more than that number of points. We cannot conjecture that this is empty because this is trivially false, but we can conjecture that this is finite. This is the strong conjecture. The strong, sorry, it's not Lang, I'm sorry. There is a strong Lang conjecture. This is called the strong uniformity conjecture. It is not attributed to Lang, even though he knew it quite well. I don't know who to attribute this one to. I actually don't know. So there exists a number such that for every number field K, the following set is finite. And as daring as it may sound, this is open. Okay? And there are several weakenings of this you can think of, and they're all open. So even if you ask if there exists a bound that depends on G and the field, such that every curve of genus G defined over that field does not have more than that number of rational points, even that is open. So the reason why I put that on the board is that I wanted to explain, well, I also want to relate it to something else at the end of the talk, but I wanted to somehow put the most, provoking conjecture. And maybe I should have said that Falting's theorem actually came as a surprise. So, who knows, maybe this is true. But so now that I've told you this conjecture, let me tell you what we know about uniform boundedness of rational points actually, what we actually know after many years of progress on the field. The last year or 2 years have seen a really, amazing progress. Certainly not due to me. Let me tell you the state-of-the-art result about boundedness of rational points, which is, so it's not just one theorem, but I will state it in only one statement. Now, this is dating 2021. Some paper already appeared in the highest top journals like Annals, and something has not appeared yet. So let me just say 2022. By Dimitrov, Gao, and Habeger, and separately Kühne. Joining their results, this is what we know, that for every genus G, there exists a constant which they denote by C and depends only on G, or nothing else, such that for any number field K, and for any curve of genus G defined over K, the set of its rational points has cardinality bounded by the following constant. We take C to the G, I should have said that C is at least 1. C to the G raised to the power 1 plus, and here is the new thing that comes out, a number rho of C. The number rho of C, I erased. The number rho of C is the rank. Remember, we had the Jacobian of the curve. And the set of its rational points. A nice group, a abelian group. One big achievement due to Mordell and Weil is that this group is a finitely generated abelian group of the form Z to the rho, and this is the same rho, plus torsion. And the theorem is that rho is finite. So rho of C is exactly the rank of this. Torsion also is finite, but we don't care. So the rank of a finitely generated abelian group is the rank of the free part. So J of C of K is an infinite set. The abelian variety has infinitely many rational points. The Jacobian is an abelian variety, but they form a finitely generated group. And this is the exponent that is in here, which depends on the field. Okay, this does depend on the field. Actually, it's not known. It's not known. This depends on the field. It's denoted this way by the others, but it depends on the field. And so that's the best result we have. And it actually was a big breakthrough. Okay. And well, I have just a little bit of time to tell you what they do to prove it, just because that will explain my efforts before. To prove it, they use this setup, this very setup, as I was mentioning before. They don't even bother to write L here. Okay, there's no L. So they take the setup. There's also another Jacobi embedding that goes this way. This is the same that was happening for a fixed curve that I said before, but it also happens over the moduli space, which is kind of a miracle, because the embedding, I didn't say that before, but the embedding of C in the Jacobian is not unique. It's not even close to be unique. Okay, so it's not so obvious that you can do that in families, but you can. Okay, again, there isn't just one way to put a curve inside its Jacobian, but there is a universal Abbe-Jacobi map. And so in this setting, they can transfer the techniques that were used to prove the Falting theorem and work quite hard to obtain that bound. And just for the experts, let me say there's one piece of technicality that I didn't explain, but I think it ought to be explained. One thing they also need to use, somebody before was asking me if I was I think was you, if we are allowing singularities, basically. Well, here is where we must, because to make things work, this space is not a projective variety. This is not compact. And to make the theory of heights, essentially the Weil machine of heights work, we have to place this inside a compactification, which is also a moduli space for singular curves. And that exists. That is known. That is also fine moduli space. So this is where the four orders get to work. And that's the setting they use. So indeed, it was expected to work, but it's a huge work. Okay. So before I finish, I have, I think, a little. How much time do I have? Okay. So before I finish, so 10 minutes is fine. I want to relate all of this together. And to do that, I want to speak about varieties of higher dimension.
So just one thing. I guess it's not known that fixed K, the rank is down.
No, it's conjectured. It's not known. It is conjectured. It is conjectured to be bounded, but it's not known. So this doesn't even prove the weak. Exactly, if that was your question. No, this does not prove not even the weak uniformity conjecture where the K is fixed. Okay, other questions? CG does not depend on K, no. And G only depends on G. Yeah, no, it does not depend on K. So, the void, actually, the void as approach. Yes, the void. No, that was the question, right? No, the void as approach. Yeah. Or proof. The void as proof. Let's call it what it is, right? So I was saying, so let's consider a variety of higher dimension. And what do we know about rational points on a variety of higher dimension? So if V has any dimension, so let's take any V. What about V of K? It's certainly not finite. This is easy. But so the conjecture is, the thing is that V of, so that's, okay, let's try to be. So here is, I'm going to go a little bit fast, and so I have only a few minutes left. So a curve C has genus G, has genus at least 2. This is a geometric condition that is clearly only valid for curves. We don't have anything like the genus for higher dimensional varieties. So the right way to redefine this in a way that it's equivalent, can be said also for varieties of higher dimension, is to say that C is of general type. And this is a technical notion that I will not define. I will only tell you what's behind it, just to convey the idea that it's a geometric issue. A varieties of general type, if its cotangent bundle has, say, let me put it very roughly, lots of sections, okay? The cotangent bundle of a variety of general type must have lots of sections, and so do its powers. Okay, let's leave it there. I can answer all questions later. For example, projective space is not of general type, an abelian variety is not of general type. But if you take the random projective variety in projective space, that will be of general type, because if you take very high degrees, you get something of general type. So this is where general comes from, I guess. Okay. Anyway, so how do we? We might conjecture that for varieties of general type, we can say something about rational points. And this is the long conjecture that I was erroneously stating before. The conjecture is the following. This is actually the strong Lang conjecture, and goes as follows. So let me just make it clear. We know very little. So this is really something difficult. The strong Lang conjecture says that if V is of general type, defined over Q, then it contains a closed subset. Then there exists a closed subset, closed in the Zariski topology, whatever that is. That's the topology we use in algebraic geometry. Closed. Which contains all but finitely many rational points of V over any field, such that for any number field K, all but finitely many, let me write it in symbol, all but finitely many rational points of V are contained in Z. So just subtract a set Fk finite, which depends on K. Fk finite. Okay. This is, again, just like the strong uniformity conjecture. This is the most audacious, daring conjecture in the field. It's open. It's true for curves. I leave that as an exercise for you. It's known to hold for curves. That's a trivial consequence of Falting's, a very trivial consequence of Falting's theorem. But there's no other evidence. In fact, I'm not sure people believe that. Okay, but that has also been there for a long time. And the connection is, that the strong Lang conjecture implies the strong uniformity conjecture. That's the connection between the two things, which is why they're interesting, because they either you prove one and you prove the other, you disprove one and you disprove the other, which is, since these two conjectures have been there for a long time, and they're both very strong, in fact. So that's the theorem that was proved in 2 stages with Harris and Mazur. This is 2 papers, one in 1997 and a recent one, although this is the important one, which is where the main breakthrough was, which says simply that the strong Lang conjecture implies the strong uniformity conjecture. So this is the link. And all the proof is all moduli spaces, all of it entirely, all with moduli spaces. And the new piece that is, as I said, this is the main one. That's the same that Angelo was saying when he introduced me with his very nice words. The piece we added is disappeared in the board, but it has to do with something we actually claimed in the paper, but didn't prove it, and has to do with it's actually having to do with the finiteness of curves up to isomorphisms over or number field over its algebraic closure. That's the thing that was proved now. So the full strong line conjecture, the full uniformity conjecture, as I stated it here, it is somehow obvious from the definition, the way this is strong. Of course, this is up to isomorphism over K, because an isomorphism over K preserves the rational points. What we did prove was over the same, but not over K bar. So this is what we proved in 1997, and this is the additional result, which is, as I said, not the main part, to be fair. But that's the connection. And since all of these things are still open, I thought it was interesting to talk about it. Thank you. Yes. Which theorem? Because yeah, I didn't write it. Yes, G, all genus, all okay. G at least 2. I didn't write it down.
To MG. Okay. Yeah. Okay. All right.
No. No. Well, yeah. So if for all G greater or equal than 2.
Okay. Thanks.
This is the first proof, and this is the new one. Which case?
Over K bar. Over K bar.
Yes.
So there you showed that existence of NG, or you precisely calculated the lower bound NG?
No, we show the existence of NG. There's okay. No effectiveness.
Okay.
No effectiveness. Yes, and this is a very good point.
Okay.
We don't know how to produce, so the proof is highly ineffective.
Okay.
Yeah.
Thank you.
Yes.
Can any of this be adapted to say something about ranks of elliptic curves? Because we don't know the boundedness of those.
I mean, if the answer were yes, people would have done it. I mean, I mean it. So I know. So there are conjectures. So a lot of this has been applied to rank of elliptic curves, but still it's not known. So the answer is yes, and it has been. So if you're looking for an open problem in that area, it might be risky because there are people working on it. In particular, the 4 authors here. So I actually don't know. It's really not something I know so well, but I know there has been a lot of work.
Using the Lamb conjecture to
Using
yeah,
something like an argument of this kind. So this technique with the universal modular space and whatsoever.
Yeah, no, he did. As far as the Lamb conjecture, there are some results also for conjectural results for assuming the Lamb conjecture, some variations of it for the rank of elliptic curves. Yes, that has been done. And since it's not so recent, I actually don't remember exactly. But there are no definite results. I thought you were asking about definite results, not conditional results.
No, I was just saying if these techniques have a parallel for the work, because this is all genus greater or equal to 2.
Yeah. So for genus 1, things get much more difficult. So yes, the difficulties can be circumvented, and they have the same answer. So let me not repeat what I just said. Yes.
Things.
Well, there are some breakthroughs, okay? I'm not sure, but we have been working on it. We have been reading these papers. We have a running seminar in Roma 3, and for now I don't see much. There are some small breakthroughs. So this is, you know, I'm not sure. But anyways, these are breakthroughs, so we're studying them. That's what we're doing. I'm not working on them right now, apart from what I already did. So this fix here is again moduli spaces. So the techniques are, well, we should be very thankful to a colleague, Jacob Stix, who helped us in the proof. But there aren't, to be fair, in this respect, so here, that many new breakthroughs. I don't think so, to be fair. But those are breakthroughs. Those are really breakthroughs, and so I thought it was worth talking about them.
Va bene, ringraziamo allora molto Lucia, ci ha fatto molto piacere.